Hello, everyone, and welcome to today's webinar, Scattergraph Principles and Practice. This is part 4 of the multi-part webinar series. In today's session, we will cover pump stations, siphons, valves, and other structures. My name is Eric Lott. I'm the marketing manager here at ADS, and I'll be serving as your host today. As always, we really appreciate you joining us for our webinars. Today's speaker is Kevin Infinker. Kevin is a product manager at ADS with 25 years of experience in environmental engineering and consulting. He's worked as a project manager, project engineer, region engineer, and most recently as a product manager for us here at ADS. Kevin is a registered professional engineer in 6 states, a member of the American Society of Civil Engineers and the Water Environment Federation. He has authored numerous technical papers and presented numerous presentations through these organizations to advance the science of wastewater collection systems evaluation. So thank you, Kevin, for your ongoing contribution to our industry, and especially today for the time and effort in preparing the information for this webinar. So without any further introduction, Kevin, we'll turn it over to you.
Thank you, Eric, and thank you for joining us today. It's a pleasure to have you back with us for our Part 4 webinar. And this has been a multi-part webinar series on Scattergraph Principles and Practice. And I want to remind everyone of the overall purpose and goal of this series, and that is to learn how to use scattergraphs of flow depth and velocity data from a flow monitor to understand the various flow conditions that are observed in what I call the urban sewer environment. And I know that many people, when I talk to people throughout the industry and throughout the United States and other places, when we talk about scattergraph techniques for evaluating flow monitor data, people are generally interested, they're generally engaged, but you also see some bit of puzzlement or wonder or mystery about the process. And I just want to let you know that there's really not a ton of mystery to it. It's all based on good engineering principles and good data. And when you put all that together, what you wind up with is a process and procedure for extracting good information about what's happening in a sewer. So the whole point of this series right here is really to take the mystery out of scattergraphs for you. But anytime we look at a scattergraph, there's a couple of questions we need to answer and ask ourselves, and that's, what do these scattergraphs tell us, and what are the implications of that? And if we keep that in mind, we're usually going to be led to the right answer in a scattergraph. So this is part 4 in this webinar series. So in part 1, we covered some of the fundamentals, which included the Manning equation and the ideal conditions we would expect in the sewer. In part 2, we actually covered backwater and surcharge conditions. Those are less ideal conditions, but we often know that they happen in sewers. During that webinar, we introduced the concept of an operating capacity. Then we had the Part 3 webinar series where we talked about sanitary sewer overflows, or SSOs, and combined sewer overflows, or CSOs. And for both of those Part 2 and 3 webinar series, we introduced a feature of a scattergraph called an ISO-Q line, or an iso-quantity line, that helped us interpret that information. And then with this scattergraph series, or this version of the webinar, we're going to talk about using some of those same techniques to evaluate nearby structures, such as pump stations and siphons, and use the data from a gravity sewer nearby to assess the performance of that structure. So it turns out that gravity sewers actually can provide some insight into nearby structures under certain conditions. And those certain conditions actually are the backwater and surcharge conditions that are caused by those structures. So anytime these structures are present, the presence of backwater and surcharge conditions in the upstream sewer that results from that structure can provide insight into how those particular structures operate. I've mentioned in some of the previous webinars as well that one of the keys to understanding scattergraphs of flow monitoring data is to be able to visualize from the data what is happening in the sewer itself. So I'm showing you some profile views here as if you're looking at the sewer line from the side. And if you can recognize what these patterns or these physical scenarios look like on a scattergraph or flow monitor data, that's a very powerful way to start to be proficient at understanding what these scattergraphs mean. So we've talked about these before, the backwater and surcharge conditions, in the last 2 webinars, and we're going to see more of this today. And it turns out it's the scattergraph that helps to visualize what's happening here. So I'm showing you data here from an 18-inch sewer. This one happens to be in Tennessee. And you can see that we have some data that is surcharge data above the crown of the pipe in the adjacent manhole, and some data that operates within the pipe. We can plot a Manning equation on here. And here I'm using a method that we talked about during the first webinar, part 1, which is the Lanphier-Cole method, where I have fit a portion of this data to the Manning equation. And you can see where it agrees and where it disagrees with the Manning equation tells us important things about what's going on. So here we see with the data and the Manning equation plotted together, there's 3 distinct regions. Where the 2 agree is where we have uniform flow conditions. So everything above, say, about 9 inches and below, in this particular sewer, operates under uniform flow. Above that, actual conditions are deeper and slower than we expect. That's called a backwater condition, much like you would have in a lake upstream from a dam in a river. And then anything above the crown of the pipe that's flow accumulating up into the adjacent manholes, that is a surcharge condition. You can see all of that illustrated here. The other technique that we've introduced in the last couple of parts in the scattergraph series is these ISOQ lines or ISO quantity lines. And an ISOQ is simply a line of constant quantity. So I'm showing 3 of those here. One's representing the minimum flow rate of this data set, which is 0.5 million gallons per day, or MGD. One is representing the flow rate at which the backwater occurs, and that is 2.07 MGD. And the other represents the projected capacity of this pipe if there were no backwater present. In other words, it's the top of that Manning equation at 3.83 MGD. And we've talked about how these ISOQs can be used in 2 different ways. One, they can be used to illustrate the flow rates that occur under certain hydraulic conditions of interest, like this backwater zone here that I'm highlighting here with my cursor. Or they can be used to figure out, if you have a certain hydraulic condition, what's the flow rate that occurs there as well. So let's take a look at some of the topics we want to cover today. We'll start out with pump stations. So pump stations, as you know, are often sprinkled throughout a wastewater collection system. And in many cases, what we have is a wet well at the end of a sewer line, and then that wet well has certain operating levels where pumps come on or off. And they will cycle back through. Obviously, if the flow increases, the more pumps can come on. So let's say we have a 3-pump station. Day in and day out, it may run with just 1 pump coming on and off periodically. If the flow goes up, it can run 2 pumps at once, and worst case, all 3 may come on. And they do that to match the levels in the wet well and pump accordingly. Now you can see sometimes the wet well levels will actually spill over, if you will, into the incoming sewer. I'm showing you an example of that here, where one of the operating levels of this pump station comes up high enough that you get a backwater effect, as I'm showing here, into the incoming sewer. And that, if you have a flow monitor that operates within the backwater influence of that wet well, can tell you important things about how this particular pump station is operating. So let's take a look at an example. So here's data from a 36-inch diameter sewer. This one happens to come from Texas. You see some things on this scattergraph that look familiar, and you see some that looks like a lot of data points scattered across a pretty wide area. So what is this data? What does it mean? And is it valid? Well, let's use some of the tools and techniques that we've talked about in some of the previous earlier stages of this webinar series. The first thing that I usually like to do is put a Manning equation on this graph. And you'll notice here I've done that with the Lanford-Cole method. And you can see that data, or that curve, goes right through this data in a very nice manner and gives us a full pipe condition right up here. But you'll notice we never quite achieve that. We start to see backwater and surcharge conditions before that happens. We can mark those conditions here off to the right. Now you'll notice another thing that's kind of unique happening on this graph is this region right in here, this depth range. You'll notice some of the data operates on the Manning curve. That means it falls under uniform flow conditions. But some of those very same depths right over here operate deeper and slower than you would expect. So that's a backwater condition. And those actually don't exist at the same time. Those exist at different points of time. And what's happening here is I have this sewer upstream of a pump station that part of the time these depths between 18 and 24 inches are going under uniform flow conditions, and part they're in backwater. Everything above that is all in backwater, and then above full pipe, of course, you're in surcharge conditions. Now, let's take another tool that we have at our disposal, and that's the ISOQ lines, and we can plot a few of these of interest. So down here at the bottom, I have the minimum flow plotted. It happens to be 1 million gallons per day here. I also have another one plotted at 9 million gallons per day. This happens to be the capacity of this pump station with one pump running. So you'll notice here the data falls along this ISOQ line. And then the maximum capacity of this pump station, the rated capacity, is 16 million gallons per day. I got these two numbers from the municipality. I plotted those numbers on here. And you'll notice what's happening is that day in and day out, you typically don't see this full capacity on this station, this daily capacity coming in. And when you hit that level, this sewer goes into backwater. And you can see it follows that flow rate, which is the pumping capacity of the station at the time, up until you get about here. At this time, another pump kicks on, causes the velocity to go up and the flow rate to go up. And now I'm operating here along this 16 MGD curve. In some cases, I'm operating a little further to the right, better than expected. And then what will happen is this will continue to climb. As the flow rate drops, the pump is still pumping at the same rate, so it will eventually draw this flow down at 16 MGD and back to the pipe curve, or this Manning curve. And then it'll continue to drop here as the flow rate decreases, and it'll operate back in here. And so some of the interesting things we discovered from this particular one is obviously most pump stations have a lead pump that alternates between two different pumps. So one pump operates as the lead pump for a while. Later on, maybe the next day, the next pump operates as the lead pump. Various ways of doing that. But you'll notice visually, in effect, I almost have two ISOQ patterns here when this one pump comes on at about 9 million gallons per day. And what's happening here is one is one lead pump and one is the other. And that tells me that in this case, the two lead pumps were not pumping the same capacity. And this is something we noted to the municipality, and they were able to go check that out. The other insights you get out of here is looking at the maximum capacity the station is pumping, which you can see it draws the flow back down at 16 million gallons per day. And notice we have more capacity in this pipeline. So it tells me the pump station itself is the limiting factor here, not the pipeline coming to it. And that we could actually expand this station up to about 23.5 million gallons per day pumping capacity if the need was there for that. that gives you an idea of some of the insights that you can get from looking at a scattergraph in a gravity sewer near a pump station. We're going to look at a couple of more pump station examples here. So here's another one. This one happens to sit at a wastewater treatment plant. This gravity sewer happens to be just upstream of the influent pump station. So this particular data set comes from another 36-inch diameter sewer. This one happens to be in Indiana, if I remember correctly. You'll notice we have a totally different pattern here. And it's not something we have typically seen in some of our other examples. But let's use some of the tools we have at hand to make sense out of it. The first thing I want to do is apply a Manning curve to this. And I'm going to use the design method. So that means I went back to the municipality and I said, can you tell me the slope of this sewer? And then I assumed the roughness value and I plotted this curve. And you'll notice that the data comes close to this curve but doesn't quite agree to it, which tells me that this data is all either in backwater condition or very close or briefly in uniform flow conditions. You can see I've got a little bit of uniform flow marked here where it just touches this curve, but a lot of that is backwater as well. And what's happening here at this pump station is they are actually using the incoming line to the wastewater plant for flow equalization. So they're storing water in this particular trunk line and then pumping it down as they choose to for process operation at the plant. You can see they do allow this line to surcharge. This data was collected during typical dry weather flows, so there's not any rain events shown here. But this is a 5-pump station, and we actually took the capacity of those lead pumps running in typical dry day fashion, and you can see they run from anywhere from 2.5 to 4.2 million gallons per day. But depending on what level they're operating at, you can see a good example of an ISOQ at work. This one ISOQ represents 4.2 million gallons per day. So any point at anywhere on this curve represents 4.2 million gallons per day of flow. So I could be at 12 inches of depth and 3 feet per second right here, and that is 4.2 million gallons per day in a 36-inch pipe. Likewise, I could be at full pipe and only 1 foot per second, and that also is 4.2 million gallons per day. So that's a good example. The actual interceptor or trunk line leading into this plant, you can see the projected capacity is up to 16.5 MGD, so they do have a lot of extra capacity here. When they allow those pumps to run and work, this data would run up this particular curve rather than like they're controlling it here. So some more good insight from a different type of pump station. Now, I found another example that I thought was really interesting to look at. This is quite unique, and this is what data looks like upstream from a pump station with variable frequency drives. So these stations, you don't find them as often, and this is one of the few I've actually run across where I've had a flow monitor just upstream from it. This one comes from a pump station in Indiana, and you can see here we have data from a 60-inch diameter sewer. But you see some really interesting patterns here. And a typical station with variable frequency drives, what they're trying to do is vary the pumping rate of a given pump such that it keeps the level at about the same level while that pump or that combination of pumps is running. And you see that here in this data where we see data clustered in certain depth regions on this graph. So let's use again the tools that we have available on the scattergraph to take a closer look at this. The very first thing I can do is I can plot a Manning curve on here. You can see at the lowest flow rates that we see, the lowest depths we see in this pump station, I should say, The Manning equation fits this data very well. But the other data, it does not fit in the same manner. That tells us we have different hydraulics going on at different times. So we have uniform flow where the two agree. At depths above that, up to full pipe, we have backwater conditions with some interesting things going on. And then above that, we have our surcharge conditions with some more interesting things going on. If we want to take a closer look at this, we can actually plot a variety of ISO-Q lines here. I've actually plotted quite a few on here. And what I did is I went back to the municipality and asked them what the different pumping combination rates were. And I actually plotted those on here in conjunction with the data. And it turns out that this station has five pumps, all with variable frequency drives, and they can operate in combination of one, or pump 1 and 2, 3-pump combination, a 4-pump combination, and all 5. And what you see here is actually all 5 pumps running, 4 of the pumps running, 3 of the pumps running, and then this is a combination of 2 or 1 pump running down here. So what happens is this data, once it gets high enough, this site goes into backwater. You can see it does that at about 20 million gallons per day, this third ISO-Q. And then it runs up to here. And then it holds in that combination right here. And then if the flow rate exceeds a certain amount, it starts climbing an extra pump will kick on to 28 MGD, and we'll start climbing this ISO-Q. And if the flow rate continues to go up, it'll match that and turn another pump on, and we will go up to 40 MGD. And we will stabilize here. And then if we start to get more flow coming in from that, it will start to accumulate because we're maxed out on the capacity of this station, which is 40 million gallons per day. Eventually, if the flow rates abate, that 5-pump combination can pull the flow down. It'll hold here. It'll pull it down, hold here, pull it down, hold here, and it'll pull it down again until we're back to normal. Now, what I thought was kind of interesting with this example here is you'll notice the data points climbing up here are spaced out farther than they are coming down here. And that tells us that when we're moving up these ISO-Qs, we're moving up at a faster rate than we are when we're coming down. Just an interesting little observation there. But this is some very interesting data here and shows you the complexity of the hydraulics upstream from a station like this. But with a little bit of extra information from the municipality or the consulting engineer that you might be working with, along with your scattergraph tools like the Manning equation and some ISO-Q lines, you can learn some interesting things either about how the station is performing, or the people that are controlling the station can learn some interesting things about how the station itself is impacting the upstream line. So very interesting case there. So we've looked at 3 pump stations. Now let's go back and look at something different. Let's look at an inverted siphon. Some people call these inverted siphons. Some people call them depressed sewers. Some people just generically refer to them as siphons. You'll hear me use the term inverted siphon today just for consistency. A siphon, or an inverted siphon, is something that we use in the wastewater business to get gravity flow under some type of obstruction, something that's in the way. It could be a stream or a creek. It could be a river. It could be a railroad track, anything of that nature. And so the inverted siphon is designed to route flow under something, but still uses gravity flow to push data through that structure. It often does that by taking the flow and routing it into a smaller pipe, and then having multiple pipes available to move flow through the siphon and under the obstruction that's in the way. So I'm showing you here flow entering an inlet structure or an inlet chamber to an inverted siphon. If you look at that from the pipe's point of view, you'll see that flow is routed into a smaller barrel, and then if the flow gets high enough, it will actually crest a weir and allow it to enter the second barrel. So they use this multiple barrel system to provide one barrel for most of the flow, most of the time, and then you bring other barrels online as the flow increases to accommodate the full capacity. And the trick, of course, with siphons is making sure that they have enough velocity to get the flow through the siphon without depositing a lot of debris. Obviously, a lot of these siphons fail in that regard because they can become problematic, and most of you that have them know that they can be difficult to maintain. Let's take a look at what data looks like just upstream from an inverted siphon. So here's an example. This is a data from a 12-inch diameter sewer. Happens to be upstream from a double barrel siphon, and this one happens to be in Texas. So again, it's a slightly different looking scattergraph than you're accustomed to seeing, but let's use the tools that we have at hand to make sense of it. The first piece of that is let's take a look at what the Manning equation tells us. So I went back to this municipality and I said I need to get the design or as-built slope of this particular line. I'm estimating a roughness. I used the design method to draw a curve on this pipe, a Manning equation. You can see that curve is plotted here, and the only place it agrees with the data is at full pipe. I've also taken the Manning equation and used the Siphons method to plot this curve right here. And you'll see it fits most of the data until I get up to about 10 inches or so. So the fact here that most of my data fits this Siphons curve. I have what we call a dead dog, which is indicative of some type of downstream obstruction to the flow. That tells me I have backwater conditions at all times here when the flow is less than full pipe. Of course, I have a little bit of surcharge conditions above here. I can also use ISO-Q lines to tell me a little bit more about what's going on here. So here's my minimum flow rate, 0.2 million gallons per day. This inflection point here I've got marked off by 1.4 million gallons per day, and basically what I did is I moved this ISO-Q around until it matched up with this departure condition right here, where the data is departing from this Manning curve right here. And then I took my full pipe capacity based on the design method, and I plotted this capacity, which is 2.7 million gallons per day. Now, it turns out that this inflection point is actually the flow crossing over the weir, which means we completely used the capacity of the first barrel in this particular siphon, and flow is now moving into the second barrel. And how you do this analysis here is this flow rate tells me that right here, the maximum capacity of the first barrel of the siphon. And it turns out this one has two 8-inch barrels in it. So if you do the math there, 1.4 million gallons per day running full through an 8-inch siphon barrel gives you a barrel velocity of 6.2 feet per second. Now, for those of you that have operated siphons or designed them, typically the target value is 3 feet per second in the siphon barrels. So this one, when it's running full capacity, actually exceeds that. That's a good thing. Now, when we run full, we're running at 2.7 million gallons per day. That means I have 1.4 going through the first barrel, and it means that I have 1.3 million gallons per day going through the second barrel. So you can do the math there on the second barrel, and that's 5.76 feet per second. Again, that's a good thing. Now, one of the other things I can plot on here with an ISO-Q line is my maximum dry day flow rate. I did this through another analytical tool we have called Slicer, which separates the flow into dry weather and wet weather flows. And for this particular pipe, my maximum dry day flow or the maximum flow that's going through the siphon day in and day out, is 0.5 million gallons per day. So, again, that is a full siphon barrel because it's running below the grade line. If you do the math on there, that day in and day out, that siphon barrel is only running at 2.22 feet per second, which is below our 3.0 design guidance we would like to have. And what that tells me is this siphon probably has trouble from time to time with debris settling out in it, and it's probably a cleaning issue for this particular customer. So that's how you can take this technique, data from an upstream sewer, a little bit of knowledge about the downstream structure, and evaluate its performance. Now, I've got one other interesting example to show you today, and that's a knife gate valve. Some people may just refer to this as a knife gate. Here's a diagram of what that looks like. In this case, this is a partially closed or partially open knife gate, and you can see what it looks like from a profile view and from a view looking down the sewer, cross-section view. Now, as you can imagine, as the depth gets high enough in this sewer, the knife gate itself starts to induce backwater that we can see at an upstream monitor. So here's data upstream from a knife gate valve. This one happens to be at a location in Illinois. And again, you see some patterns that look somewhat familiar, but they're a little different from anything else we've seen before. So again, take the tools that we have. The very first thing is the Manning equation. So I plot that on this data set using the Siphons shoot spot curve, and you see where it agrees with that up to about 9 inches or so, and then it disagrees with it. So something else is happening there. Since we have a quote-unquote dead dog here that the Siphons shoot spot method illustrates, that means we have backwater conditions at all times up to full pipe, and then above that, of course, we have surcharge conditions. If we add our ISO-Q lines on here, I'm showing you the minimum flow rate, which is 0.6 MGD. I'm showing you the flow rate that occurs at this inflection point in the data. So hydraulically, something is happening here. I'm showing you an ISO-Q that is met before we get to full pipe. That's at 6.4 million gallons per day. And again, these two ISO-Qs, I actually arrived at those numbers by plotting them on the graph here and moving them around by changing the flow rate to find out the flow rate at these conditions that I was interested in finding. Then I've got another one here showing you the flow rate at the projected capacity of this sewer line if we were not to have this backwater present. Now, I'm showing you here on this diagram the knife gate added to this particular data set. And once you do this, you can actually see a little bit more clearly what the data is telling us. So once we get up to about 10 or 12 inches, you can see that the knife gate becomes an obstruction to the flow, and it causes the data to become deeper and slower than we expect. Now, this spot here, above 18 inches, where the data starts to follow this ISO-Q line again, you'll notice that's about the same point where this knife gate starts to close in completely on the cross-section of pipe. So everything above here in the pipe is impacted by the knife gate. Now the question becomes, why would this knife gate be here? It's causing obstruction. It's causing a problem. Under the right circumstances, it could cause an SSO. Turns out this knife gate happened to be installed at a boundary point between an agency and a satellite agency. So you have one community discharging into another. And the downstream community was getting a little bit concerned about, well, I would say more than a little bit, they were concerned about the amount of I&I they were seeing from their upstream customer. And to regulate that, they actually put a knife gate in at a certain position. And the result here is what you have here. And as you can imagine, what this could do is change the place an overflow might occur from down in the primary receiving agency's collection system to a point upstream in the satellite agency's system. And there's a lot of dilemmas there with that scenario. Some of them involve some legal issues that are beyond my capabilities, but just from a hydraulic or a technical basis, the knife gate is a restriction to the flow. And so the question really becomes to me is, okay, what happens if you take this knife gate out under this particular scenario with this data? And it turns out you can take this data, drop it down this ISO-Q line, and it will fall all the way back here to this Manning curve, which means it'll fall to a depth right about here, which is quite amazing that gate here was causing this much of an issue. So the gate here was meant to be a way to regulate flow, but I think in this case it turned into a case where it was actually causing more problems or harm than good. So best in my mind to keep these types of structures out of the system because they can be problematic, and you can see the dramatic effect that this one was causing here. So a few key points to remember when you're looking at nearby structures is that gravity sewers can actually provide insight into the performance of what I call adjacent structures when they're operating under backwater conditions caused by them. So with some knowledge of the adjacent structure and how it's expected to operate, flow monitor data can actually allow you to compare actual versus expected operation and gain some insight into how the actual structure is performing. You can actually do the reverse as well, and people that are familiar with looking at controls on structures like this, they can actually see how when they change control settings, what kind of impact they have on the upstream sewers. So examples of this that we've talked about today include pump stations, inverted siphons, and knife gate valves. And I'm sure you can probably think of another structure or two to which this concept could extend as well. So those are the key points to remember from today. If you would like to look at this a little bit more in detail, Pat Stevens and I wrote a paper along these lines a number of years ago, and that paper is available. It was published in the proceedings of an ASCE conference, and we can make that available to you if you'd like it. I keep coming back to the Scattergraph Principles and Practice poster. Many of you have have a copy of this already. Basically, in this webinar series, we've been walking through the different elements of this poster. And what we have covered today is actually the first three examples on the fourth line of the poster. If you don't have a copy of this and you would like one, you can get one through our website at adsenv.com/scattergraph. We don't have any more hard copies available at the moment, but you can download a high-resolution PDF file for your use. Now, if you'd like to join us in a couple of weeks, we're going to actually proceed to part 5 of this webinar series. And that part 5 deals with subcritical and supercritical flow. In part 1, if you remember, we covered a lot of detail about the Manning equation. Part 2, we introduced ISO quantity or ISO-Q lines, and have used them extensively in part 2, 3, and 4. We're going to continue to use those in part 5, but we're going to add a new feature or a new tool called the ISO Froud or the ISO Fluid line, and use that to examine subcritical and supercritical flow in sewers. Following that, we'll have a webinar on flow monitor performance, and we'll conclude this Scattergraph series with a technique to evaluate self-cleansing conditions in existing sewers. So I hope you'll be able to join us for the remaining 3. And with that, Eric, I think we probably have a few questions, and I'm going to turn this over to you.
Thank you, Kevin. Yeah, we do have several questions. We'll now move directly into the Q&A time. Of course, we promise to follow up with you after the webinar if we don't address your specific question. First question, Kevin, is actually two parts. The first is, what if my pump station wet well operating levels are all below the invert elevation of the incoming sewer? Can I still evaluate the pump station using this methodology?
Yeah, so good question. And the simple answer to that is no. So if you recall, the whole premise of this method is that the flow monitor must operate within backwater and or surcharge conditions that are caused by a pump station wet well in order for the ISO-Q lines that we're using to actually represent the pumping rates of the various pump combinations for that station. However, in the case that you're asking about, that's actually a good thing because it means that the pump station does not dictate the operating capacity of the upstream sewer. So it's the upstream sewer that's able to push everything that's coming its way into that wet well without being hindered. So that in and of itself is a good thing, but you cannot use the ISO-Q method to evaluate what's happening there.
Okay, the second question is, how far away can a pump station or inverted siphon be to evaluate it effectively?
Okay, so we had a similar question regarding to how far downstream we can see SSOs or sanitary sewer overflows and CSOs. And in a similar fashion, the question is not so much a matter of distance as it is a matter of whether or not the monitor location experiences backwater influence from the nearby structure. So if it does, there's good insight that can be gained. However, unlike the SSOs, we don't always know where an SSO is going to occur. However, we almost always know where these pump stations and these other structures are in the system. So if you're looking to evaluate one of them, I recommend that you get that monitor as close to that structure as possible, and you'll be able to maximize what the insights you'll be able to gain.
Okay, question number 3. What if multiple sewer lines enter a wet well or inverted siphon inlet structure? How does this affect the analysis?
Okay, it does complicate things a little bit. So if you have multiple lines that enter, say, a pump station wet well or that are coming into a siphon inlet structure, each one of those sewer lines, if you were to monitor each one, one of those lines, you should still be able to get good information about the depths at which different combinations of pumps engage or different siphon barrels engage. However, you actually have to monitor all of those lines in order for the flow rates to match up with the pumping rates or the barrel capacities of the entire structure. So basically, if you're only monitoring, let's say you have 2 lines coming into a wet well, but you're only monitoring one of those with a gravity sewer, what's going to happen is the flow rates that you're seeing in one gravity sewer are only proportional to the total flow that pump station is pumping. And you don't know what proportion you have unless you're monitoring all of the incoming lines. So in some scenarios, that may just mean deploying a couple of monitors. However, that can be problematic on some stations, like you have like a small pumping station that maybe has 3 lines coming into it. That's where things can get a little tricky. But that's basically, to use this technique, you need to be monitoring all of the lines that are involved. So it works best for stations or structures that have 1 main line coming in, or maybe 2 at most, is where the situation, the analysis technique makes most sense.
Okay, we'll make that our last question today. Of course, we'd love to continue to receive your questions related to scattergraphs. We appreciate every single question you submit, and we've had a bunch over this series. So if you have a question or if you'd like additional information on what Kevin covered today, you can email me at elot@idexcorp.com. My email address is on the screen. And thank you very much for your attendance, and this will conclude today's webinar.